Good morning, Maz. Week 4, study guide questions. Here we go. Bring them in. Let's get to it. All right. We're on micromechanical failure now. So making our way. Here's number 1. Failure of unidirectional composite subject to longitudinal tension. Okay, so we're pulling along the length of the fibers, driven by the strain to failure of the constituent fiber and matrix materials. In case 1, where the strain to failure matrix greater than the strain to failure of the fibers, here, the failure stresses are given. And this critical volume fraction is given as the volume fraction in which the failure mode sort of shifts, okay? Or the calculation of how this thing fails sort of shifts, all right? So that's case 1. That's the case where the fibers are more brittle. The matrix has a higher strain to failure, all right? Fiber is more brittle. Okay, and then case 2, where the strain to failure of the fibers is greater than strain to failure of the matrix, okay? So matrix more brittle. We have these sort of equations that govern the strength of the composite given a certain volume fraction of the constituents. All right. So what we're asked to do here is derive the critical volume fraction for case number 2. So you want to find VF crit for case 2. Okay. Well, essentially these two equations here, which govern how the composite fails in case number 2, are just two linear equations, right? And what we're looking for is the critical volume fraction where those two things are equal. All right, so it's pretty simple, pretty straight ahead, like how to go about doing this. And you just more or less want to set equations equal. And solve for VF crit. Okay. So let's do that. Let's maybe call this equation number 1. This is equation number 2. And so let's just go at it. I'm going to just look at the right-hand sides of both equations here and set them equal to each other. So F1T prime VF plus FMT VM equals F1T VF. So this is, left-hand side here, this is equation number 1. And right-hand side here, this is equation number 2. That's more or less it. All right. You just want to solve for VF here, and that is VF crit. Okay, so there is some algebra that you can work through here. You're trying to isolate VF, so you probably want to get all terms with VF on one side. So I'm going to do F1T prime VF. I'm going to move this over. This will be minus F1T VF plus FMT times VM, which is 1 minus VF, equals 0. All right, remember that the matrix volume fraction is 1 minus the fiber volume fraction. Okay. So let's extract all the VF terms here. So VF is F1T prime minus F1T, and then minus FMT. Plus FMT equals 0. All right, so we solve for VF, which is going to be VF crit. And this is going to be negative FMT over All this will be in the denominator. FF1T prime minus FF1T minus FMT. Okay, but one other way that you can consider doing this is you could rearrange these two terms together, make this a plus sign. Okay, so that would sort of take out the negative of all this thing. And if you switch this sign here from a negative to a plus, you can get rid of this negative sign here. So this will end up being plus. Yeah, you just basically want to switch the sign you basically want to multiply all this by -1. If you multiply both the top and the bottom by -1, you'll get FMT over here. This will be F1T plus FMT minus F1T prime. And this is your answer. Okay, so that is the answer here. That is the critical volume fraction where you have a shift in sort of the way that the material responds and behaves when you're pulling it in longitudinal tension. So let's go to the notes here. It might be useful to kind of look at the notes here and look at the summary. So I pulled up this slide here. This is kind of the summary of all cases for longitudinal tension. So case number 1, the fibers are more brittle. Sort of depends on if you have a very high or very low volume fraction. You can work your way through. If the fibers are more brittle with a high volume fraction, you have a certain strength. For low volume fraction, you have a certain strength. And this equation here dictates whether you're using this equation for high volume fraction or this equation with low volume fraction. It's similar over here. It said VF crit found in homework exercise. We just did that. All right. So this is slide 10 of the longitudinal tension notes. So that's that. Okay, that's problem number 1. Let's move on. Let's go to problem number 2. Okay, maybe need to do it in 2 parts here. So we've got this graph that tells information about the constituent materials that are going to make up a particular composite. All right, we've got a stress strain curves of composite constituent materials. So we have stress strain curve of epoxy, that's here. You have stress strain curve of S glass fibers, which is here, and stress strain curve of boron fibers, which is here. These values that are given in these charts, these are XY coordinates of the end of the line. Okay, so that's what's given. Let's see what the questions are about this. Here it says plot the longitudinal tensile strength. Let's bring it in here. So this is what we're trying to find for this particular problem. Plot longitudinal tensile strength of a boron epoxy composite as a function of fiber volume fraction. Okay, so what we want to do is we want to plot where the y-axis is F1T. It's the longitudinal tensile strength of the unidirectional composite. And then the x-axis is the volume fraction of boron. This is the general idea. Okay. Calculate the critical volume fraction where the failure mode shifts from matrix dominated to fiber dominated. Okay, so this is just getting back to this sort of flow chart for understanding how longitudinal tension works. So when you have these like longitudinal tensile type problems, you need to understand, all right, are my fibers more brittle? Is my matrix more brittle? And am I below or above the critical volume fraction? Once you figure those 2 things out, you can sort of follow the pathway down to see which equation you should use to calculate strength. All right, so let's think first, are our fibers more brittle or is our matrix more brittle? Well, what does it mean to be more brittle? It's just all about strain to failure. So here, our epoxy has a strain to failure of 0.3. And if we're using boron fibers, which we have over here, then the boron fiber strain to failure is 0.008. So in this particular case, we have that the fibers are more brittle than the matrix, right? So in this situation, fiber is more brittle. Since the strain to failure of the fibers in tension is less than the strain to failure of the matrix in tension, right? That's generally how we label these things. So what that means is, if we go back to our little flow chart here, the fibers are more brittle, so that means we have case 1. Okay. All right, that's good. This problem, though, is asking us to plot the tensile strength as a function of fiber volume fraction. So we have a fiber volume fraction that can range from 0 to 1. Okay. 0 is 0% fibers, meaning it's all matrix. 1 is 100% fibers, meaning that it's all fibers, right? We can sort of think about, well, what are the extremes going to be in that case? Well, if there's 0 fibers, that means that the failure strength of the composite will be the failure strength of the matrix in tension, FMT, right? Similarly, if you have 100% fibers and you plot what's happening there, it should be pretty obvious that the failure strength of the composite is just going to be the failure strength of the fibers, because if it's all fibers, 100% fiber, then it's just the failure strength of the fiber. So this is the failure of the fiber in tension, right? The failure of the matrix in tension, we know what that is because we have the stress strain curves of the matrix, okay? So in this case, the failure of the matrix in tension is 20 KSI. So we know straight away that this extreme value is going to be 20 KSI on the far left-hand side. Similarly, the failure of the fibers, we know this maximum point here to be 450 KSI. So this point over here is 450 KSI. Right? The question is, what is the line that connects them? So what are the points that sort of make up the locus between the two, right? Now, we know that there's a critical volume fraction where the failure mode kind of shifts. So if we bring in our flowchart here again, it says, all right, the fibers are more brittle. In the case where the volume fraction is low, VF below VF crit, then the equation that governs how this thing fails is just F1T is FMT VM. All right, so let's write that down. FMTVM. Now, this problem asks us to plot in terms of volume fraction, not in terms of matrix fraction. So you probably want to convert this to matrix fraction, right? So converting to matrix fraction, FMT times 1 minus VF, right? The matrix fraction and the volume fraction of fibers are, must equal 100%. So this is a reasonable type look, all right? You can sort of simplify this a little bit further, and you'll get negative FMTVF plus FMT. This is a linear equation. With an intercept here. And here is your slope. If you were to just plot what this looked like by itself, the intercept is FMT, that's here. And the slope is negative FMT. And once this value equals 1, then the entire thing is equal to 0. Hopefully that's pretty obvious to see. So at a value where VF equal 1, this goes to 0, and so this is just a linear equation that looks just like that, right? So that is for low volume fraction. So it's going to be values of VF that are kind of in this region here. Now let's look at the other side of the coin, the high volume fraction. Bring in our flowchart again. If volume fraction is high, so VF greater than VF critical, we have this sort of equation that governs the failure. All right. FF1T VF plus FMT prime VM, where FMT prime is this general equation here. Okay, so let's get that down here. I'm going to write this in terms of volume fraction. Rearrange slightly. And here we are. This is again a linear equation again in VF. Okay. And if VF is equal to 0, what's going to happen? Well, we're going to have an intercept here with FMT prime. So here, this is your intercept. And this here is your slope. Okay. Hopefully that's clear. If you plot this on the same graph as first equation that we put together for low volume fraction, you'll see something that looks like this. So these are the two equations that together make up the possible failures for this composite that we fabricate. Right here, the point where they touch each other, this is VF crit. It is the volume fraction that shifts the failure mode from one governed by low volume fraction to one governed by high volume fraction, right? Now, what the problem asks you to do is to plot this. So you'd have to put in the numbers for these guys, which, okay, just figure out, you have all the numbers. So just put the numbers in and plot this thing. If you do that, you should end up with a plot that looks a bit like this. Okay, so we see kind of these two equations that I'm talking about. Here, this is the one that is governed by low volume fraction. This is the one that's given for high volume fraction. And so if we actually wanted the failure of this guy, we're going to take the higher of the two strengths. So the actual line that sort of dictates or tells us what our failure is here. So this is the line that generally governs how this thing responds. It asks us to calculate the longitudinal strength if you fabricate it with the critical volume fraction. Okay, so let's calculate the critical volume fraction. Remember that VF crit for case 2 is FMT minus FMT prime all over, let me erase the string mark here, FF1T plus FMT minus FMT prime. Okay, you really want to punch everything in here. I guess we can do that. Failure of the matrix in tension. All right, let's come up here back to our graph. Failure of the matrix in tension is 20 KSI. Minus FMT prime. So let's calculate FMT prime. Remember, FMT prime is EM EF1T. So the elastic modulus of the matrix, this is stress divided by strain. So of the matrix, this is 20 over 0.03. Oh, I don't have my calculator with me. 20 over 0.03. Oh boy, it's going to be like 6.7. 667. Times the failure strength of the fiber in tension. That's 0.008. Okay, so FMT prime is 5.33. Okay, so minus 5.33 KSI, all divided by FF1T. Okay, FF1T, let's go up here. The failure strength of the fiber in the one direction in tension is 450 KSI. Plus FMT, failure strength of the matrix in tension, we know is 20 KSI, minus FMT, 5.33. You do all this, you'll calculate the critical volume fraction to be 3.2%. So that is the value at which we shift from one to the next. That is this value here, 3.2%, or, if you don't want it in terms of percentage, 0.032. All right, so that's that. Okay, that's problem number 2. Okay, let's continue on, and let's look at problem number 3. This is related to problem number 2, except it just uses different constituents. So instead of a boron epoxy composite, which we had in problem number 2, we're going to do the same thing for an S-glass epoxy composite. Okay. So instead of using boron in epoxy, which is here's boron, here's epoxy, what we're going to do is we're going to use the S-glass fibers now in epoxy. So we're going to look at this fiber with this matrix material. Right? The difference now is that we have a different sort of case. So out here, you see the strain to failure of the fibers is like 0.04, and the strain to failure of the matrix is 0.03. So in this particular case, when we're looking at S-glass fibers and epoxy, you have a different type of failure. And now we have case 2, where matrix is more brittle. So we're more or less going to go through the exact same procedure as we did for the last problem, except we have matrix more brittle rather than fiber more brittle. So what that means is if you just go back to that sort of flow chart that I made in the slides, we're looking now at case 2 instead of case 1. So we're going to make a plot of this line and this line, overlay them on top of each other, and see what the critical volume fraction is, and et cetera, et cetera, et cetera. All right. So it's a very similar procedure. Calculate the longitudinal tensile strength with 50% volume fraction fibers. All right. So let's do that. We know we're in case 2. And then the question is, do we have VF greater than or less than the critical volume fraction? So we need to calculate what the critical volume fraction is. So in case 2, VF crit This is in your equation sheet. Let's bring this in. This is from your equation sheet, the critical volume fraction. We also solve for this in problem number 1. FMT over FF1T plus FMT minus FF1T prime. Right. So we need FF1T prime. Let's calculate that here quickly. The elastic modulus of the fiber in the one direction, this is stress divided by strain of the fiber in the one direction in tension, multiplied by the strain to failure of the matrix in tension. So let's go back up to the graph. The strain to failure of the matrix in tension, this is 0.03. And then this elastic modulus of this guy, it's rise over run of this line is the elastic modulus. So it's just this point here. Kind of the slope of this line will be stress over strain of that particular line. So it's going to be 500 KSI divided by 0.04. Okay. So that I can punch in here. It's 12.5 MSI. All right. So here this is going to look like I said, 500 KSI divided by 0.04. It's the strain to failure of the fibers in the one direction in tension, and all this times 0.03. You work this, you'll get F1T prime of 375 KSI. Okay, so back up here. Let's finish this off. We'll do the numerator first. FF1T, failure strength of the fibers in the one direction in tension. This is 500 KSI. So 500 plus failure strength of the matrix in tension. I think that's 20 KSI. Let me go back up here and make sure. Yeah, 20 KSI here. FF1T prime, we just calculated. 375. And the numerator, FMT, failure strength of the matrix in tension, says 20. You work this, the critical volume fraction, and calculate that the critical volume fraction in this case is 13.8%. All right, so this is the critical volume fraction. We're told that the composite has a 50% volume fraction. So given VF is 50%, we have VF greater than VF crit. So we know our pathway down our failure envelope now. We have case 2, the matrix is more brittle, and we have that the volume fraction is greater than the critical volume fraction. Okay, so this is the equation that's going to dictate our failure. F1T is FF1T VF. I know all these things. FF1T is 500 KSI. And I know the volume fraction here is 0.5. So 250 KSI. And that's my answer for number 1. Clear? Or for part A, not part A. Let's move on to part B. Estimate the transverse tensile strength of 50% volume fraction boron and 50% volume fraction S glass epoxy composite. And it tells us to use stress concentration factor. Okay, let's do it. Need a little coffee. We're now looking at transverse tensile strength. So now we want F2T. All right. And it's asking us for one thing, for boron epoxy and for the other constituents. So let's start with the boron epoxy first, and let's look at F2T. So F2T, this is the transverse tensile strength. So you created a unidirectional composite, but now you're pulling across the fibers, right? So, in longitudinal tension, you're pulling along the length of the fibers. So that is, I don't have a good picture of it here, but yeah, pulling along the fiber length. And here you're pulling across the fibers. This is the two direction of the composite, right? So if we make our little model of a composite, right, a unidirectional composite. So here's your unidirectional composite. All your fibers are kind of moving in this general direction. Remember what our coordinate system typically is. We say 1, 2, 3 is very common, right? So the one direction, this is in the direction of the fibers. That's the one direction. And then the two direction is this way. So if you kind of look at a cross section and look at how the two direction would look when it's under failure, it looks something like this, right? Here are the individual fibers that exist inside of the composite. You pull across the two direction and you start to see like this transverse tensile failure, something like this, right? So transverse tension failure is really governed by stress concentrations around the fiber. So if you're pulling this thing, you start to see like around the outer edges of these fibers, that's where the cracks start to come in and where this thing starts to fail. That's because you have these stress concentrations, okay? So the stress concentration factor associated with having fibers inside of a matrix is derived in a couple of different ways. There's what's called the strain concentration factor or the stress concentration factor. The stress concentration factor is this form, the strain concentration factor of this form. It's not really important that you know 100% where this comes from or why it's derived in this way. Just say that it has something to do with the properties of the materials, the constituents, and also how densely packed the fibers are inside of the composite, right? That's why you see like the volume fraction term sort of pop in here, right? Okay. So in general then, F2T is going to be FMT over K sigma, or, the strain concentration factor. So either the stress concentration factor or the strain concentration factor. It's just the failure strength of the matrix and tension divided by that factor, right? So if we go back to the problem statement, it says use stress concentration factor, not strain concentration factor. So stress concentration factor is this K sigma term. So that's what we're going to end up using. So for the boron epoxy composite, we have F2T equals FMT over K sigma for boron. Okay. Failure strength of the matrix and tension. Go back up to my graph. Failure strength of the matrix and tension, 20 KSI. Divided by stress concentration for boron. All right. You would have to calculate this, right? So the stress concentration factor, like I showed in the notes, uses a lot of different information about the composite, including the elastic modulus of the matrix, the elastic modulus of the fiber in the two direction, and then volume fraction. So all of these things are known. You know all of these things. Volume fraction is 50%. Elastic modulus of the matrix you can get from the graph of the constituents. Elastic modulus of the fiber in the two direction you can get from the graph. So all these things are known. So you can calculate K sigma. All right. So you could calculate this. I think it's going to be approximately 2. So the answer, if you sort of work this out fully, for the boron epoxy composite is 8.36 KSI. And then for the second bit, for glass, so this is K sigma of glass. Work this again, the failure strength of the matrix and the tension doesn't change. This is divided by, again, approximately 2. If you work through this, oh, sorry, this is boron. Epoxy. This is glass. Epoxy. This will end up being 9.3. Sorry. Okay. Let's keep going with this problem. There's a part C. What is the ratio of longitudinal tensile strength to transverse tensile strength for each of these two composites? All right, well, we have both of these numbers. So we want F1T of boron divided by F2T of boron. You have F1T from problem number 2. You have F2T from problem number 3. Okay, so you work these two things together. Failure strength in the one direction and tension of boron is 227. You had that from the first problem. So the ratio here for boron is 27.2. And F1T of glass over F2T glass at 50% is 26.9. So this is the ratio of longitudinal to transverse tensile strength. Pretty significant difference, right? Whether I pull along the length of the fibers or across the fibers makes quite a large difference. Right? Let's cap off this problem. Part D, are the ratios you found at C relatively large or relatively small? Well, talked about this. This is a big difference. So 27 times stronger in the one direction than it is in the two direction. All right, so that's pretty significant difference. Okay, I'm going to call it here. Problems 1, 2, and 3. These all work with unidirectional composites. Okay, I'll do the rest of the problems, which deal with the next topic, which is lamina failure. So multiple sort of like a larger scale sort of thing. I'll deal with those in a separate video. Okay, chat with you soon.